For literally thousands of years, electricity and magnetism were kind of like two strangers living in the same house. They just never spoke to each other. One was that crackle of static electricity, and the other was the weird, invisible pull of a magnet. Then, back in 1820, a complete accident in a classroom finally introduced them. And that one introduction, well, it went on to power our entire world.
I mean, think about it. For the longest time, nobody even suspected these two forces were related. It took one single, chance observation to completely shatter a 2,000-year-old idea, and believe it or not, kickstart the modern electric age.
And that brings us to the guy who literally stumbled upon one of the most important discoveries in the history of science.
What I really love about this story is just how ordinary the whole setting was. So it's 1820. A Danish physicist, Hans Christian Ørsted, is in the middle of a totally normal lecture. He's got a wire, he's running an electric current through it, and just sitting on the table nearby is a simple magnetic compass. He flicks the switch on, and for just a split second, he sees the compass needle twitch. Now that wasn't supposed to happen. It wasn't part of the demo at all. But he saw it, he investigated, and his conclusion was absolutely earth-shattering. The electric current was creating its own magnetic field.
And really, this all boils down to one simple, beautiful idea. Moving electric charges, which is, just what we call an electric current, they don't just flow from point A to point B. As they move, they generate this invisible field of magnetism all around them. This was the birth of electromagnetism.
Okay, so this discovery immediately leads to another question. If a current makes a magnetic field, what happens when you put another moving charge into that field? Well, this is where things get a little weird.
So let's really think about that. You've got a magnetic field, and you fire a single charged particle right through it. What's going to happen? Does it speed up, slow down, or just sail right on through untouched?
Well, the answer is it feels a force. We call it the Lorentz force. And for our purposes, we're just looking at the magnetic part. So F is the force, Q is the particle's charge, V is how fast it's going, and B is the magnetic field. But the real secret sauce here is that little X in the formula. That X means it's a cross product, which is just a fancy way of saying this force doesn't push or pull in the direction you'd ever expect.
But this is a fantastic little trick to help you visualize it. It's called the right-hand rule. Seriously, you can do it right now. Point your fingers in the direction the particle is moving. Then curl your fingers toward the direction of the magnetic field. Now stick your thumb out. The direction your thumb is pointing, that's the direction of the force. And notice, your thumb is pointing completely sideways, perpendicular to the other two.
And this is what makes the magnetic force so strange. An electric force is totally straightforward. It just pushes or pulls a charge right along the field lines. Easy. But the magnetic force? Nope. It's a sideways push. It doesn't make the particle go faster or slower, it just deflects it. It forces it to turn.
Okay, so we know what happens to one particle. But what happens when we scale this whole thing up? What happens when we take two whole wires, each with a massive stream of moving charges, and put them next to each other? All right, check this out, because this is cool. The first wire creates its magnetic field, which circles around the second wire. Now, since that second wire also has a current, it's full of moving charges. It feels that weird sideways Lorentz force, and in this case, that sideways force pushes it directly toward the first wire. They literally pull each other closer. So the rule here is completely counterintuitive. Currents moving in the same direction attract, and currents moving in opposite directions repel. This is the exact opposite of what we all learned about static charges, where like repels like. It's totally backwards. In fact, this force is so real and so fundamental that it's actually how we define our unit of current, the ampere. That's right, the official definition of 1 amp is based on the precise amount of force it creates between two wires that are 1 meter apart. It's all built on that strange sideways push.
So now we get the force. The next logical question is, can we control it? Can we shape the magnetic field that creates that force?
And the answer is yes, absolutely. It all starts with the shape of the wire. A single straight wire gives you these big circular field lines. But if you bend that wire into a loop, you can see the field starts to get focused right in the middle. And then, if you stack many loops together, you get something incredibly useful, a solenoid.
And you can see the transformation right here. On the left, with just one loop, the field is kind of messy, bowing outwards. But look at the right. When we stack hundreds of those loops into a solenoid, all those individual fields add up to create this super powerful, straight, and incredibly uniform magnetic field on the inside. At the same time, the field on the outside becomes almost nothing.
What this really means is that the solenoid is our #1 tool for creating a perfect magnetic field right where we want it, whenever we want it. You just run a current through it and, boom, a strong, uniform field appears. This simple little device is a cornerstone of modern tech.
And now for the grand finale. Let's put everything together. We've got a loop of current, and we know how to make a nice, uniform magnetic field. So what happens when we combine them? Well, we get motion.
Let's break this down real quick. So we place our current loop inside that magnetic field. Look at the forces. The force on one side of the loop is pushing up, but the force on the other side is pushing down. The net force is 0. The loop isn't going to fly off the table, but it experiences this powerful twisting force. And that's what we call torque.
And this right here, this is the heart of every electric motor. You send a current into a coil of wire. The magnetic field pushes on the sides of that coil, up on one side, down on the other. That creates a torque. That torque makes the coil spin, and with a clever little switch to keep reversing the current at just the right moment, you can get it to spin continuously. And this just shows you the incredible power of a single idea. Every single electric motor, the one in your toy car, your blender, your fan, even the one in a massive electric vehicle, it's all just a more advanced version of this one basic principle. A loop of current will spin in a magnetic field. All of it, everything, goes right back to Oersted's little accident.
So yeah, it all started with a compass needle that twitched when it wasn't supposed to. A moment of pure chance that connected two fundamental forces and literally changed the course of human history. It really makes you wonder, doesn't it? What are the happy accidents happening in labs right now that are going to define the world of tomorrow?